When you're writing programs with objects, you often want to make use of an object's built-in capabilities. You need to interact with it and carry out operations on it. Well, how do you know what capabilities an object has? Those are defined in the class that an object is an instance of. So remember, every object is an instance of some class, and that class definition defines not only the attributes or the properties that make up some object, but also its capabilities through what are called methods. A method you can think of as a function that's defined in the context of a class. And once it's defined in the context of a class, all objects of that class now have this capability associated with them, such that you can say, have an object and call upon some capability by calling a method that's built into that object's class. Let's make this more concrete with some real examples and jump right into code. I'm going to encourage you to set up a file just like I've got here. And I've named mine ls22_methods.py, and I've placed it in a lessons directory, but you can organize yours how you'd like. And I would encourage going ahead and reproducing the code that I've got in the screen up until this point, and pausing the video here so that we can catch up just as soon as you're ready. All right. So this is a continuation from the previous example that we ended last lesson with, where we're defining a class. So this is the definition of a class, and we're modeling a 2D point in the 2D Cartesian coordinate system. We have two attributes defined in this class, an X and a Y attribute, and both are floating points. So notice we're grouping two variables together and saying that, okay, anything that is a point is going to have these two variables built into it, X and Y. We think of these as attributes in Python, but you'll hear them also called instance variables or properties in other programming language contexts. Additionally, as we learned in the last lesson, we've got a constructor defined. And in Python, we name this constructor _init. It's a special method whose name is _init. And what we learned is that this first parameter self is a special parameter in the Python language that is given a reference to a new object on the heap that is going to be our responsibility for initializing. So the point of the constructor is to establish an object and get it ready for use. And we have two more parameters defined on this constructor because we'd really like to be able to establish the X and the Y attributes of our point objects as soon as we construct it. All we're doing is assigning to the X attribute of the object that is being constructed whatever the X parameter was, and same with Y. Down on line 19, we see that we're actually making use of this constructor. And here we're saying, okay, I want to call this function that looks like a function call, but when we see, well, what is the function point? We see it's actually not a function at all. It's a class definition. And so because of that, there's this convention that we're going to call upon the constructor and establish this object. And 1 would be the argument that corresponds to X, and 2 is the argument that corresponds to the Y parameter. And you're wondering, well, where is self? And as we discussed, this is automatically set up for us as a reference behind the scenes, right, in this constructor call. Then, for the purposes of this example, I'm just printing the A point object using an F string literal. And so this will print A colon and then the string representation of A. And the last thing we discussed at the end of the last lesson was that when you try and use an object as a string, Python will automatically call the repr method, right? So this is a method that's a magic method built into the Python language, _repr, short for representation. And it's given a reference to the object that the method is called on. And so here we're trying to represent the object A would be assigned to self. The same reference would be assigned in both places. And we return a string that is the X and Y. So I'm going to go ahead and try running this example by running ls22_methods. And we see that we print out A, 1.0, 2.0. Those are the X and the Y attributes of this point. Just to catch up, if we were to imagine what's going on in memory, by the time we reach to line 20, so imagine that we're paused at line 20, we would establish that the name point is bound to a class whose definitions are on lines 3 through 16. And this variable A is going to be established as a reference to a new point object whose X and Y attributes are 1.0 and 2.0. Now there would normally be a constructor frame set up here where we would jump in, we would pass our parameters and set everything up. For the purposes of this video, I've elided that, so it won't be shown, but that would work just as we looked through in the previous lesson. And I'll link to that lesson in the comments below. All right. So what we'd like to do in this is imagine how can we scale a point? If we want to imagine like what would happen if we multiplied both components, the x and the y component, by some number. And maybe for the purposes of the type of program we're writing, this would be a common thing that we would want to do. So without methods, one of the things we could do is we could just say something like, okay, a dot x is going to be scaled by a factor of 2, and a dot y is going to be scaled by a factor of 2, right? And what this would do is it would change the x and the y attributes of a. If we wanted to imagine what this actually looks like in memory, after line 20, we would say, okay, take x and multiply it by 2 and reassign that back to itself, so 2.0. And then a dot y, take the current value of a dot y, so a, follow the arrow, y, is 2, multiplied by 2 would be 4, and reassigned back to itself, and that would be 4.0, all right? So this is what we're trying to accomplish, and imagine that this is a very common operation. It seems like, you know, if we'd like to be able to scale a point by some factor, this should be an operation that's built into the idea of every point object. Because what would happen if we accidentally forgot to scale the y coordinate? We only scaled the x. And should it really take, you know, every time we want to do this, writing 2 extra lines of code? Couldn't we build this idea into the point class? And sure enough, yes, this is the point of having methods available to us. So I'm going to reset this example really quickly, and then let's try adding a scale function to this example. All right. Sorry, I should say a scale method. So if we're going to define a method, we need to do so within the context of an existing class. And here's the class point. So I'm going to start this new method definition just a few lines below my repr method and name this scale by. And when we're writing methods, for reasons we'll discuss it in full depth again, the first parameter's name is always self, and you're not going to assign a type to self because the type is always going to be the same as the class here. Right? So then we're going to define our parameters. So let's set a scaling factor that's going to be, say, another floating point. And let's imagine that this is a method that doesn't return anything. It just changes the point by scaling both of its attributes, right? So now we can say self.x is multiplied by this factor and reassigned back to itself, and self.y is multiplied by this factor and reassigned back to itself, right? This is a method definition. It looks and feels a lot like a function definition with a couple of key differences. One, it's being defined inside the context of a class. That's one of the most important differences between just a plain old function and a method. And two, this self parameter is special. And because it's a method, it's going to be established automatically on our behalf. And we'll look at how it's established in just a moment. So how do we actually make use of this, this method that we've defined? Well, now we can say a dot, and you'll notice in the auto completion, our editor already recognizes, oh, scale by is a method that you define. So this is a capability that you've added to this idea of every point object. So we can say scale by, and 2.0 was our previous example, all right? And so now when we print A, we will see that its X and Y attributes are scaled by 2. So I'm going to try running this example again, and we get 2, 4, right? Okay, well, we leaped to a number of conclusions here without actually digging into the weeds of how does this actually work? How do we know what self is? And how does this method call actually get processed in memory? So I want to step through that process line by line here. We are at the point of reaching line 24. And now the question is, what happens when this method call is encountered? What is Python doing behind the scenes? Well, one, how do we recognize something's a method call? Typically what you'll see is, some object, A, dot, and so the dot operator is saying, hey, A is saying, okay, we've got this reference, and dot is saying, okay, we're going to go turn our focus toward the actual object that we're working with. So dot, scale by. And then we see these parentheses that give us some indication that this looks like we're making a function call, but it's got this prefix of a dot, and that object dot method name parentheses arguments is how you can discern a method call from a function call. A function call wouldn't have the object dot in front of it, right? Now we're asking, okay, well, how do we know what scale by is? And is this actually even a valid method for this object? So we need to look at what is the type of object that we're referencing. So a dot brings us to the object, and we see, oh, this is an object whose type is point, right? It was constructed using the point constructor. So we look in the point class and we see, is there a method named scale by defined? And yes, we just defined it. Then we're going to check, does it have the right parameters to be used in this way? Well, self is automatically going to be established in a means we'll talk about shortly. And any other parameter is going to need a corresponding argument. And so here we've got an argument that's a single argument of type float, and that corresponds to the single parameter of type float in this definition. So we should be good to go. Let's actually set up a frame for processing this method call. Let's go ahead and when we establish a frame, we're going to write in the name of the class, followed by a hash symbol, and the name of the method. So this is scale by. Right? And then we're going to set up a return address as we would with any other function call. The return address is line 24. That's where we're going to return back to. And now we need to set up our parameters. So the self parameter is special, and then we're going to have factor. Let's go ahead and fill in factor just to get that out of the way so that we can focus on what's really important here. Factor was this 2.0, and that's being passed into the factor parameter. So 2.0 is the value of factor. All right, so here's the key million-dollar question when we're thinking about method calls. What is self? And where does it come from? Again, the key distinction between a function call and a method call is prior to this method's name, we had some object reference followed by a dot. What self is going to be is whatever came before that dot, right? So if we look at what is A, well, A in globals was this reference to point. So self in this scale by frame is also going to be a reference to that same point, right? And so this is what's really neat about method calls. We address the object, kind of like the subject, like, hey, A, I want to scale you by 2.0. And this is where the name object-oriented programming comes from. We've reoriented this call so that it's not a function that comes first, it's the object we're addressing that comes first. And we've oriented the way we're going to design our programs around, well, what are the capabilities of our objects? So we've got our subject, that's A, our verb is scale by, and then the extra information is our argument here, 2.0, right? So we jump into this method now, and here we see self.x. So self.x is self dot, we follow the arrow, and then x is 1.0, multiply that by factor. Factor is 2.0, this would change x to be 2.0. And same idea with the next line, which is self.y, multiplied by 2.0. So that's going to be 4.0, reassigned back to itself. And so notice that by using a reference here named self that refers to the same object as A in globals, we can actually mutate and change the attributes inside of a method and build in this capability to every object of this class. Now this is a method that is kind of like a procedure. It doesn't return anything. So our return value here is going to be none. And when we jump back to line 24, we've completed this method call. And now we go on and we print A. And this would ultimately lead to an implicit method call to the repr method. We're not going to represent that here, but we saw already that this worked out. Actually, let's reconvince ourselves that this all works out and run this one more time. Boom, 2 and 4. All right. So this is an example of a method that mutates the contents of the object you call it on. This isn't uncommon, right? When you use lists, append, or pop, you're mutating that list object that you're working with. There's another way to design methods, which is to say, hey, I want to have a method that doesn't mutate the object that I've called this method on, but gives me back a brand new object instead, so that I hadn't changed anything about the original. We've fundamentally changed the original A here. We've lost the values 1 and 2 when we scaled by 2.0. But what if we wanted to be able to, scale a point and get back a new point instead? How can we do that? Well, in order to write a method that uses the class that it's defined on as one of its types, we're going to need to make use of some upcoming functionality in the Python language. And this is a funky little thing that we need to write at the top of our program in order to make use of this and use these types. So what we're going to write is from future import annotations. And this feels kind of strange, right? So future is this double underscore word here. This really means from future version of Python. This is not an experimental feature per se, but one that hasn't officially been adopted into the Python 3.9 version of the language that we have currently. But it's well established and known that this feature is going to be necessary and is coming down the pipe, and we can start making use of it today. And it's this annotations feature, which is short for annotations is when we use like this is going to return the string type, or this parameter is of type float. Those are what we call annotations in Python. So we're importing some annotation capabilities from the future, and we need to do that in order to do what we're about to see on this next example. So let's try adding another method here that is scale. And it's going to be given a self parameter just because it's a method like every other method. And it's going to be given a factor that's a float, just like we had in scale by. But this is not going to return none. This is going to give back to us a brand new point reference, right? So this is not going to mutate the point that it's called on, right? So how would we make this happen? Well, I'm going to show you this in a couple of steps, and then we'll simplify this down. Let's imagine we've got an x local variable that is going to be self.x times factor, and a y local variable in this method. That's going to be the same idea with y. And then what we'll do is we'll set up a point p that's a point, and it's going to be a point with x and y, and we will return p, right? And let's just consider for a moment the differences between these two methods. And maybe add in a docstring that describes example method that mutates object it is called on. And this one we can say scale is an example method that does not mutate object called on. And so the idea is, if you want to scale a point, well, we'll just set up a brand new point that has that scale and give you a reference back to it so that you haven't changed the original point. You've still got that point if you needed to use it later and to know your starting point. But these are two different ways of achieving very similar outcomes, but with some trade-offs we'll discuss in a little bit more detail shortly. So, okay, let's keep our example as we had it. And now what we're going to do is try setting up a B point. That is going to be a.scale. So notice not scale by. Scale is going to be given also a 2.0. So we're going to double it. And then let's go ahead and print f string b and b, right? So to continue with this example, what we're seeing here is, we mutated a in this first scale by method call. And then we added this other method scale. And when we call it, we're not going to change anything about a. So we expect, a to still be 2, 4, when we get to line 38. And B, we expect to be 4, 8, right? Because it was A scaled twice. And we'll come back and look at what actually happens in memory and some of the fundamental differences between these two methods in just a moment. So let's go ahead and try running this example and convincing ourselves that our reasoning was correct. So yeah, so A, notice, it was scaled once and its attributes were changed in the scale by method call. And this second method call, a.scale, this doesn't reassign anything. You don't see any self.x is reassigned to something new, self.y is reassigned to something new. No, what this example is doing is saying, we're not going to mutate A, we're not going to mutate the object that you called this method on. We're going to make a brand new object and give you that back instead. And this is a common, both of these are common strategies with common known trade-offs. So let's imagine what happens in memory on line 36. And I'm going to continue from this example we had started before. I'll switch to using yellow for what comes next. So line 36. Here we see a method call and we go through our steps. Okay, well, we know that this frame is completed, right? So we can effectively ignore it. We've just got it there as a trail of work that typically we would, if we were the computer, we would have deleted this. But for working through these diagrams, it's helpful to know how we got to where we are. So we're back in globals. That's our frame at this point, right? We're in the global scope when we're processing or evaluating line 36. And now we're asking, okay, what is A? A is this point object, so A.scale. We're going to have to see, does point have a method named scale defined on it? And yes, we just defined that method. Okay, well, self we know is going to be assigned a reference to A. And so the question is, does it have the right argument? So there's a single argument here that's corresponding to the single parameter. So we should be good to go. So let's go ahead and set this up. So we're going to set up a frame for point and scale by, or actually scale. So these are two different methods with similar names. But notice we're using some convention here. We're scaling a.scale by is going to give us a mutated A. And a.scale is giving us back a brand new point. All right, so the return address here is line 36. That's where we're going to go with an answer. That's actually one other thing before we continue on. Notice that this was just a method call statement standing on its own and a line in isolation. One of the other things we could have checked just to sort of do our type checking is notice that this is being used in an assignment statement. So this expression needs to evaluate to something that is of type point. In other words, the return type of this method better be point. And we could have checked that before we started this method call, but it checks out. That works out. So because this method returns a reference to a point, we can assign that reference to some other point or use it as a point later. Okay. We have the parameter self that we need to set up. And we know that self is going to be whatever A is in globals. So A in globals is this point. So self is also going to be a reference to that same point. And we have this factor parameter we need to set up. So this is our scaling factor. And that factor is once again 2.0, right? Now we jump into this frame, and I'm going to have to make these variable names along the bottom of my frame here. So x is going to be a local variable that is self.x. So self.x is 2 multiplied by factor, which is 2. So that's going to be 4. And then we process line 28. Y is assigned self.y. So self.y is 4 multiplied by 2 is 8. So y is going to be another local variable that is 8.0. And then on line 29, we see that we have a call to the point constructor. Now, if we were emphasizing construction in this example, I would add another frame to this diagram and jump into the init constructor that's defined up above. As we know, this constructor is just establishing the x and the y attributes. So I'm going to elide that constructor frame for this example and just say that we know at this point P is going to be assigned a new point object whose x is going to be, the x that was local in this frame, which was 4.0, and whose y is 8.0. All right. Now, we've established P is a reference to this point. And now what we need to do is return P. So the return value of this frame is going to also be a reference to that same point, right? So we're returning a reference to this point whose x is 4 and y is 8 back to line 36. So what was line 36? Well, that was this line. So the result of calling this method was a reference to this point. And we're saying B then is going to also be a reference to that returned point, right? And so what we've effectively established here is this variable B refers to the point whose x is 4 and y is 8. Notice we didn't change anything about A. We didn't mutate A in that method call. And now we have in globals, as we've finished both of these frames and we're returned back to globals, we have 2 point objects established in 2 different ways, right? So A we established in globals directly, and we mutated it by calling the scale by method on it. And B was established as sort of a byproduct or a result of saying, well, let's try defining a method that doesn't actually mutate the object it was called on, but actually produces a new object with the result of that operation carried out on it, right? So 2 different ways of achieving the same thing. And so you're probably wondering, well, which is better? And what are some of the differences? Which is better really depends on your context. But when in doubt, when you have programs that don't mutate their attributes, when you have methods that aren't mutating the attributes of the objects that those methods were called on, those method calls tend to be a little bit easier to reason about. And the reason is because you don't have to worry about something changing that you didn't expect to change in some method call behind the scenes. But that's not always the case. There are perfectly valid reasons for mutating objects based on method calls. As you know, you've used lists append and pop. Those methods mutated the list that you were working with, and there's value there. And so it's very reasonable that you might design a method like scale by that actually does intentionally mutate the object that it was called on. And this can be nice when you're trying to, move something around and you don't actually want another whole thing. Like you don't want to create something new. You actually do want to manipulate some existing object. You're not just looking for some ultimate result. You're looking to keep track of state in some system. And so both of these are completely valid ways of designing methods. When in doubt, I would encourage you to try and write methods that are immutable and don't change the attributes of the object that you're defining those methods, or the class that you're defining those methods in. But there are certainly cases where you want to mutate. Understanding the trade-offs, and one of the trade-offs is, well, notice that whenever we call scale by, we're not having to produce a whole new object. So it's probably a little bit faster to process than the scale method call if we were doing this hundreds of millions of times. And scale is going to produce a new object every time. If you need to be able to backtrack and, let's say we wanted to be sure we always had our original starting point as we did some other calculations. You could imagine writing the immutable version of this. The second example would be more beneficial. An open question is, well, wow, for something like scale, it sure seems like we would love to be able to do something like A multiplied by 2.0. But if we tried to do this, we would see that we have an error. The asterisk operator, which we tend to associate with multiplication, because when we use this with numerical data types, it multiplies. But notice it says it's not supported for types point and float. So is there a way that we can actually make this work where we would be able to say A multiplied by 2 and have that make sense in the context of our program? Well, the good news is in Python, we can do that. And that's what we'll look at in the very next video. So I hope you'll join me in the next video, which will be linked to down below as well. And there we'll look at what's called operator overloading, which allows us to write methods just like scale that will allow us to make use of these built-in operators like the asterisk operator, which can lead to some very powerful and concise programming capabilities with types that we invented and defined ourselves. Great work thinking about methods and working through these examples.